My name is Xiayun, in case you can't pronounce that. I usually go by Joy in my work, and I work in Disney streaming services, which is kind of appears a lot in the news recently. So what do? We build distributed systems. I build distributed systems at daytime. I fantasize a lot about research at nighttime. So yeah, it's a bit of brain split. So this is, I'm also talking in Scala Exchange this year, and this is actually what I am going to talk, because I will have more time there. So I'm thinking this one might be slightly rushed. If you understand everything here, then you probably can skip my talking Scala Exchange. If you don't, feel free to ask me questions afterwards, but I will probably just go really fast. Before we start, how many of you think you have a basic or decent understanding of neural networks? Okay, that's pretty good. So I go really fast. So let's start. This is the outline. So basically, I will just briefly go through what is a neural network. There are three neural networks that I will be demonstrating. And in the end, is actually what I'm most personally passionate about is why bother? Like, why bother using Scala at all while you have TensorFlow and everything? So first of all, to prove I'm not cheating, I'm only using FS2 and CATScore, okay? No other libraries. So very quickly, what is a neural network? Put very simply, it's just linear algebra. So it's basically a list of weights, which is, you can think of it as a matrix, or tensors in more fancy terms. Tensor is just multi-dimensional arrays. If any of you have advanced physics background, you would probably argue with me, but don't. Tensors are just multi-dimensional arrays. And then what makes them really special is the activation function, which I'll talk about in a bit. But you can think of this is the architecture of a network. These are your input, these are output. And you can just stack a list of hidden layers in between, where each layer is a type of weight and activation function. Okay? Oh, and just to be precise, this is a feed-forward type. There are other types like recurrent, which you actually feed the output back. Okay, so activation functions, to me, these are the crucial bits because they actually introduce non-linearity to the whole network. Because if you just stack a list of matrices, it's essentially just a linear estimator. Because if you multiply matrices, you only get a matrix in return. But if you add some activation functions in between, then you actually get very nice nonlinear approximations. And these graphs are just to show how activation functions are kind of like neurons in your brains. And that's where the name is coming from. But I think these days the analogy is kind of outdated, at least. Yeah. So the two most popular activation functions are sigmoid, which is a continuous type, so it's differentiable everywhere, but it's mostly active when you are close to 0. Okay? So if you're very, very, very negative or very, very positive, it kind of collapses you down to either 1 or -1. This is ReLU. It has a really fancy name, but it's just max of 0 and Z. Okay? So use ReLU in bars and to impress people. We'll be using sigmoid, just you will see in a moment. And once you have the architecture, how do you make everything work? So this is nothing different from all the other supervised learning training methods. So supervised learning means you actually have a training data set, and you know the correct answers to these training data set. So what you're trying to do is you want your model to predict the input as close to the answers And then you use this model to predict a test data set which you don't have answers for, and you hope it will do a good job. So the way we define it is you can compute a loss function measure between the correct answers and the predicted answers. And you are trying to minimize this distance. So the main two types of loss functions, one is mean squared error. This is really popular in like classical supervised learning methods. The other is cross entropy loss, which is really just maximum likelihood. This one is more popular in neural networks. Well, I can intuitively explain because there is a log here. And if you go back to see the activation function, a lot of times we'll have an exponential here. So these two kind of cancel each other, and math-wise this like works out. Okay? And once you have a loss measure, how do you minimize it? And then that's like very straightforward gradient descent. So you basically calculate a differential function on the surface or on the curve, and then you descend along the line. All good now? It's really fast. Okay, cool. So let's see the first neural network. So we'll be using the MNIST dataset. It's like the grandpa age dataset. The only reason I'm choosing it is because it's manageable on a single laptop. So it's an image classification task. Basically, you are trying to predict these handwritten digits. In our case, we'll just be predicting 0, just making it a binary classification task. Okay, so first we need to load the data sets, and here this is the only place I'm using FS2. So it turns out it's really easy to, as you can see, the data set is kind of weird. You have to do a bit of size counting, but it's actually really easy just to do it in FS2. You can drop the first 16 bytes, which you don't want. And then you just take, because you know the image dimension, which is 28 pixels per side, and then you just take 784 per chunk and convert it into a matrix. And that's something kind of surprised me while I was working on this code. I was like, I didn't expect this to work so well. So that's a nice thing to know. So the first neural network is kind of really straightforward. We'll use linear weights. We'll have a sigmoid, and we'll use cross-entropy loss function. And this is how I draw neural networks, because I can't use fancy graph software. So weights, inputs, this is an interim node, and bias. When you have weights, you usually just have a one-dimensional bias. And then this is a sigmoid function, and then this is a loss function. So I use J for loss notation. You might see some others in other literature. And now we want the gradient. Again, that's my handwriting. So we want, let's see, what do we want? So this is our linear model, right? This is our bias. So you can see these are the two model parameters that we want to train for. Now, this one is really easy because it's a plus. So the gradient of the final loss on bias is the same as the final loss at Z. Okay? So here is the two values that we care for. This is essentially the gradient on bias. This is essentially the gradient on the linear model itself. And this, just trust me on this. And in terms of code, it's really just translating these into code. It's nothing special. Yeah, and once you have the gradient, we basically just do a gradient descent with a learning rate. I'm actually using learning rate equal to 1. It doesn't really matter on MNIST. By the way, all this code are on GitHub. I'll show the repo in the end so you can see it. So we can run the demo. So this is the like the way you usually present your model in machine learning is number of steps and loss function. So in this case, you can see the loss function like drops pretty sharply, like very quickly, which is expected because, I mean, if you can't train on MNIST, then you're pretty much screwed. Okay. And I should mention, I think I'm using a batch size of 1,000. So this is pretty cool. So in the end, I actually try to predict the test data set, which is never seen by this model, and to see the accuracy. And we're pretty good there. So that's the first one. Questions? OK.
So I think leaky ReLU is the most popular one. What do you think?
Yes, but this is more, I guess, an introductory talk.
Oh, OK.
Yeah, I agree. Leaky ReLU is really popular these days. But yeah, we can talk more afterwards. All right, so like, what's so good about it? Nothing's good about it. But the biggest complaint I have about this methodology is you're doing math like manually, and just try to compute gradients yourself for this network, and you can't do it. And by the way, this is a ResNet, so residual network. So I think one of the variation for ResNet, you can have like more than 100 layers. So it's simply not possible to calculate gradients yourself. And so like there is an actually general way to calculate gradients, and I think it abstracts pretty nicely to, I wouldn't say functional programming, but I find it very natural to write it in Scala, which is back propagation. And essentially it's graph computation. And graph computation is pretty much a functional data structure. So I can just quickly explain how back propagation works. It's just partial derivatives. So let's say this is your output, which is loss function you can think of. So the value right now is minus 12. Okay, so the derivative of the output with regard to itself is 1. Okay, now this node has 2 input nodes. And the operation here is a multiplication. So we know the derivative, the partial derivative with regard to a multiplication is basically the other input, right? So let's, in this case, like 3 multiplies minus 4 is minus 12. So the derivative of 3 is simply the other node, which is minus 4. Okay? So vice versa. So the derivative of this node is simply the other input. Now on this node, because it's a plus, so we know the partial derivative of both inputs are just 1. And now you have to, the propagation part is you have to carry the previous gradient backwards. So the gradient on this node is minus 4. Now you know the gradient with respect to the plus operation is 1. So you basically just multiply 1 by minus 4 and so on, so until you arrive at your destination. So I think this is like fairly straightforward graph computation. We can go back to this code in a while, but like let's go through the main, the key components of the graph first. So first is node. It contains operation. So this is a node. It contains the operation. It contains the value, minus 12, which is type tensor in my code. it has a name, which is an identifier, but that's like just for internal implementation details. Okay. Now, for operations, it's basically you need to have a forward computation. So, for example, plus, you need to know how to add the two numbers together. Now, you also need to have a backward computation. You need to know how to carry the gradient back to your inputs. Okay, so you need to have a backprop. You have f. F is a forward. It's bad naming, but yeah. Okay, now the graph. The graph is the least functional part in this whole thing. So the graph basically remembers for each node who are your input nodes and who are your consumption nodes. That's it. And then with all this knowledge, you can actually compute the gradient from your last node to whichever node you're interested in. Okay, now we can go back to the main function. So this is kind of recursive, but not tail recursive thing. So it's kind of ugly. Let's see. So this function basically wants to know the gradient for a node. And then we already have like a state remembering all the gradients we've calculated so far. So, well, first of all, like if we've already calculated this node, then just return. If not, we find all the consuming nodes. So these are the nodes later in the graph. Okay, so let's say I want to calculate gradient for this. It's not been calculated before. So what do? I look at a later node and see if it's been calculated. And if it is, then I know it's 1 in this case. So the only thing I need to do is call the backprop operation on this node, which is multiplication, and then carry this 1 forward, well, backward. Okay, so we get the consuming nodes. We try to get the gradients for this node, and this is a recursive call. And then we call the backprop on this node. Like this is the crucial part. So if you do like v.op, then you're screwed. But you have to do it on the consuming nodes operation. And that's basically it. The reason it works is because you always start at the last node. So you can always find one that has been calculated. Okay? So now we have everything. How do we represent a graph? And this is where, so I struggled to find a simple way to represent a neural network close to TensorFlow syntax. And this is what I think is pretty good. So basically, you have a state monad. You have a state monad, and in the process of constructing this state monad, you basically implicitly constructed the graph itself. Okay? And then you can basically call backprop on this graph with regard to all of your input parameters. And this is pretty nice. Like this is basically our network, right? We have a matrix multiplication, we have an vector addition, and we have a cross entropy. And that's it. So, and that's the training part. As I said, it's really just calling graph.backprop. Okay, so let's see the second neural network. And this is the code for the second neural network. And like I think it's much better than all the formula before. And the training result is, as you would expect, exactly the same. It's slower. because of all the objects, but okay, so we get the same test data performance.
Sorry, why did you say the second one is slower than the first implementation?
Well, it's first of all, you are kind of doing lots of, first you have a lot more objects because node operations and graph, etc. Second, every time you calculate gradient, you are doing a recursive function. Whereas in this first case, every time you do a gradient, you're just doing math. Yeah, I think it's not. So first one, it's like 10 seconds slower, which is actually significant in this case, because it's almost double the first time. Okay, now this is. I wouldn't say this is deep learning because it's not deep at all, and the essence, like the black magic of deep learning, is more layers. So let's try the last one that my laptop can run, which is one hidden layer. There's a linear layer, sigmoid, another linear layer, sigmoid, cross entropy.
Usually, how do you decide how many layers if you want to solve a problem?
I will talk about this after we see the performance of this network first. Okay? And this is the code. Like, it's pretty nice, right? You just add 2 more lines and it works. And this is the performance, and that's the interesting part. And it's actually getting worse. I will run, but this will actually take more time. So I think the thing is you have to strike a balance between number of parameters and number of training data to answer your previous question. So in this case, MNIST, we have 60,000 training images. With this one hidden layer architecture, we actually have quite a lot of parameters. So the first model is, how much is this? This is like around 40,000 already. Then you have a 64 weights. You have another weights. So like we have around 40,000 to 50,000 parameters here, and you only have 60,000 training images. So it's kind of overfitting. It's less a problem when you have gigantic data sets. So that's why like things like a ResNet could work. But obviously I can't demonstrate ResNet here. But yeah, don't know if that answers your question. Okay, so I'm actually very happy that we can briefly talk about this. So why bother? Why bother when you just use TensorFlow? And by the way, this is the code to do the same thing in TensorFlow. And if you put on your functional programmer's glasses, what can go wrong in this code?
Debugging?
Debugging, yes. Why? Sorry, who said debugging? Okay.
I mean, in TensorFlow and the Tensor is a library which is used for the deep learning framework.
Yeah.
So they don't have very good debugger. I think TensorFlow 2.0, which is being, I think
Yeah.
next year, they're improving that.
Yeah.
So, but Scala, of course, is a language which is driven from Java, got a lot of debugging. You can
Okay.
put the breakpoint and do in that way.
So that's on the language level.
Yeah.
Yeah, so my main problem of this code is when you write it, you don't know if it's correct or not. Like, these are strings. And how do you know all the matrices have compatible shapes? You don't. So I think this is where like something more typed could help. I'm not saying Scala is the answer. It's most certainly is not. But I do think there should be something better here. And what's funny is if you follow like research papers, they mention bugs a lot, which I find very amusing because if you look at like computer science papers, people are kind of embarrassed to mention bugs because it's not supposed to be there. And this is a recent one from OpenAI. And they were basically saying, we spent a lot of time, we find this bug, which is basically, I think one of their tensors are accidentally cleared out to all zeros. And they were very happy that they found this bug, they fixed the bug, and the performance just went very good. And for me, it's not something that I would be proud of, to be honest. This is a very good article. You can look it up online. The name is Why Deep Reinforcement Learning Does Not Work Yet. And it's also mentioned like bugs, okay? So this is my personal opinion on what the most ideal research language should be like. Typed, very simple, clear syntax, which I think Python is a winner here. Native vector and parallel computation, which again, like NumPy did a lot of work. JVM is kind of behind. There is a thing called deep learning for J, which they kind of use a trick of exporting to C and C++ to do the vector computation. And a notebook environment. So Jupyter is very big in research community. The biggest problem with Jupyter is it's not version control friendly. If you have checked in Jupyter to Git, you know what I'm talking about. Visualization, Python is great. Scala is 0. And I'll be happy to hear more people's opinion on this, because this is something I actually thought about a lot. So this is basically a summary slide, like what is a neural network, how to train it, and think about how to do things better. And these are the code. That's it.